Okay? So let's take our time real quick. Before we do anything, let's identify what n is going to be. Oh, remember, k is equal to 0, 1, 2, 3, all the way up to n minus 1. We're going to identify what k is going to be. We're going to identify what our n is going to be as well. So it's the complex. This shouldn't be complex roots. I'm sorry. This is complex cube roots of this guy. So really what we're looking for are what are the values that get spit out when I do this, when I take the cube root of negative 1 plus 3i. So first things first, hopefully everybody can see, excuse me, everybody can see that n equals 3. Now, what's k going to be? Well, n is 3, and this says start at 0, right? Then go 1, then go 2. Now the question is, do I have to go up to 3? No. Well, I don't, because this says go up to n minus 1, which really makes sense. What we're going to end up with is a z sub 0. That's going to be our first complex root. We're going to have, I'm going to give myself a little bit more room. Actually, let me put those on the other page so that we have plenty of room. We're going to have a z sub 0. We're going to have a z sub 1. And then we're going to have a z sub 2. And remember, since it's a cube root, I need 3 roots. Okay, so now what do? We take a real big deep breath here. By the way, I'm going to show you what happens if you screw up and you put 3 in there or go up to 4. What happens is you get a repetition of roots. All right, so what do? The first thing that we have to do is we need to turn z equals negative 1 plus root 3i into what? Well, let's think about this for just a second. We're going to think of it as a complex number, all right? And then we're going to turn it into the polar form. So I'm going to go over 1, and I'm going to go up. Let's see, root 3 is what, 1.7-ish? So I'm just notice there's no real scale here. So this is negative 1 plus root 3i, if this is the imaginary, and this is the real, right? I need to find the modulus, or really the hypotenuse of z. That's what I'm looking for. All right, because this is z equals this. So I know that the modulus of z, which hopefully by now we realize is the r, the modulus of z, that's a terrible looking z, isn't it? The modulus of z is just the square root, sorry guys, is just the square root of negative 1 squared plus what? Root 3 squared. Well, that's pretty easy to deal with, isn't it? That's 1 plus 3, which is equal to the square root of 4, or 2. I'm going to now rewrite z as, just like I've done before, right? I'm going to rewrite z as r times cosine of theta plus I sine of theta, right? This is the polar form of this complex number. So I'm going to divide out r. Remember, this guy is our r, so I'm going to pull a 2 out. And then I'm going to multiply through. Excuse me, I'm going to multiply through, so really I'm dividing negative 1 by 2, so I get negative 1/2, right, plus root 3 over 2i. Now, if you're not confident at this point in terms of being able to, sorry you guys, let's try this again, I apologize. Negative 2 times, well, I guess, think about this. I could write this as negative 1/2 plus. I didn't make that big of an error, right? Okay, but I haven't included my cos theta yet and my sine theta. So if you're not confident at this point, if you had to, you could do, we know that tangent of theta is equal to y over x, and I could go root 3 over negative 1, which is negative root 3, and then I got to be careful here though, right? Because if I take the inverse tan of negative root 3, it's only going to spit out values in the first and the fourth quadrant, but this guy's in the second. You notice how I'm always identifying which quadrant I'm in, right? Or I could just go, wait a sec. I know, and I want to make sure you guys understand this, I know that the cosine of theta is negative 1/2. I know that the sine of theta is positive root 3 over 2. Hey, wait a sec. These are one of the fantastic 5 numbers that we pull out. Doesn't theta have to be 2 pi thirds? We don't have a choice, right? 2 pi thirds are 120 degrees. What do you want to do? The example does it with degrees. I guess we'll do it with degrees just to stay consistent. So 2 pi thirds is 120 degrees. All right, so I'm going to totally rewrite z as 2 times the cosine of 120 degrees, right, plus I sine of 120 degrees. I'm taking this nice and slow because we don't want to screw this up. Okay? Or if I wanted to, I could rewrite this as 2 cis 120 degrees if I want to be a little bit better. Okay, now we're going to follow this. Let me change colors. We're going to follow this formula right now, and we're not going to panic. All right? I'm finding z sub 0, and that is the value when k equals 0, right? So my first root is going to be what? Well, n is 3. I identified n equals 3, and I know what my k's are. And I'm just playing with k equals 0 right now, right? So z sub 0 is the nth root, so I have the cube root of 2, right? Times, now this is where we got to go easy. I'm going to go cosine of 120 degrees divided by n, right? So n was 3, true, plus 2 pi times 0 divided by 3. I'm actually going to write that out because it'll keep me from doing stupid stuff down the road. I need a little bracket here. Plus, same thing, remember? The thetas, when I rewrite in the polar form, these thetas are always the same thing. These theta naughts are what I just referred to as my thetas. So we're not afraid, right? So I sine of what? We got this 120 degrees divided by 3 plus 2 pi times 0 divided by 3. So what does this turn into? Well, it turns into the cube root of 2 times, everybody got it? It's just going to be the cosine of 40 degrees plus I sine of 40 degrees. Nothing to it, right? If I wanted to be a little fancy, this could be the cube root of 2 cis 40 degrees. Okay? Now, take a second. Just take a second. Try to do this one. I'm going to pause for just a second. And I want you to try and do z sub 1. And then I'll meet you back here in just a sec and see how you do. Okay? All right. Okay. So hopefully you gave it a try. Now, also, hopefully you caught a little error that I made. Can you see the error that I made up here? I got lucky because this thing was concealed because I multiplied by 0. But what's the error that I made? Let's put it in red. If I'm going to use degrees, then 2 pi needs to be 360 degrees, doesn't it? It's always nice to be able to catch mistakes. True? All right, so remember, if we're committing to radians, we stay in radians. And that's why I was a little hesitant over here, because I knew somehow my psyche knew, wait, if I convert it to degrees, I'll forget about the 2 pi. But that's all right, hopefully you caught it. All right, if you didn't, you're going to end up with a really strange answer when you do it down here. But let's do it together. You ready? So we got the cube root of 2 times, the cosine of 120 degrees divided by 3 plus, now check it out, 360 divided by 3 is 120, right? Now remember, for this, k was equal to 0. For this, k is equal to 1. Notice that these two always match up. This is z sub k, okay? So plus 2 pi, whoops, ooh, I almost did it again, sorry, 360, I'll write this up for this guy. It's going to be 360 times 1 divided by 3, right? And then plus I sine, and the nice thing is they're always the same angle measure, right? So 120 degrees thirds plus 360 degrees times 1 divided by 3. And then we take a minute and we clean it up. So this equals the cube root of 2 times, and here we go. Let's see, 120 degrees divided by 3 is 40 degrees. 360 degrees divided by 3 is 120, right? So doesn't this become the cosine of, let's make sure I don't, 140, 120, what is it? Excuse me, 40, 120, that's 160, right? 160 degrees plus I sine of 160 degrees. And this ends up, if you want to get fancy, it's the cube root of 2. Cis, I'm stuttering. There you go. That's kind of cool, huh? Okay, now try this guy. Take a second. Try it for k equals 2. Remember, these two always match up. So give it a shot. I'll pause for a moment and let you give it a try. Okay, Hopefully you gave it a shot. You should have paused the video, by the way. So I get the cube root of 2. It's not a bad way to practice, though, huh? No. Okay, so I get this. What am I going to do? K equals 2. Now this one gets a little bit trickier. I'm gonna finesse this guy a little bit more. So I'm going to have 120 degrees divided by 3 plus, now 360 divided by 3 is 120. So really we're doing 120 degrees times 2, right? Because there's our K right there. So times 2 plus I sine of 120 degrees divided by 3 plus 120 degrees times 2. And then we're off to the races. Cube root of root 2. Let's clean it up. Let's see, 40 degrees plus 240. What is that? Cosine of 280 degrees. Does that sound about right to you guys? Plus I sine of 280 degrees. Isn't that awesome? And I end up with the cube root of 2 if I want to be fancy. And you don't have to be fancy. I want to make sure that you understand it. Like some people freak out when they see the cis. They're like, what is that? Is that a cos that he screwed up? And I'll yell at you if I can't differentiate the cis from the cos. But this can be written as 280 degrees. Now, watch real close what happens if I let k equals 3. If k equals 3, let's do this in red. Okay? I'm not actually going to go into the whole thing. But watch what happens if k equals 3. Well, if k equals 3, then I'm multiplying 120 times 3, right, which is 360, right? And if I add 360 degrees to any angle, then I become coterminal with the angle that I started with. In other words, this is going to become 40 degrees plus 120 degrees times 3, which is affectionately known as 40 degrees times 360. Which gives me the same this turns into the same value. Notice I don't put an equals, because clearly a 400-degree angle is not the same as a 40-degree angle, but it produces the same value because it's coterminal. What happens if k equals 4? Well, we end up at this place, because if I take 40 degrees plus 120 times 4, I end up with, what is that, 480 plus 40 is 520. This is 520 degrees. Right, which is coterminal with 160 degrees. 160 plus 360 is 520. So it becomes unnecessary. Okay? Now in class tomorrow, if we have time, I'm going to go over the proof of why this works, but it's actually pretty simple. Really think about it. If I want to prove that this guy right here is the nth root of just z, of this guy right here, what would I do to prove this? If I wanted to prove that this was an actual cube root of this right here, what would I do? I'd cube it. I just take this thing and cube it, and I better get this guy back out. Now, think about this for just a sec. It's actually really easy to figure out. If I were to take this and raise it to the n, and use DeMoivre's theorem, think about what would happen. I multiply the angle through by n, wouldn't I? So all these n's would cancel. This would just become r, right? The nth root of r to the n is just r. When I multiply through by n per DeMoivre's, all the denominator n's are going to cancel, and I'll end up with theta plus 2 pi k. Well, the period of cosine happens to be 2 pi. Happens to be 2 pi. So I'm just going to keep getting theta back out. The sine of theta happens to be 2 pi, right? Or the period of sine happens to be 2 pi. So I'm going to get the same value out over and over and over again. So that's a brief outline of the proof of why this actually works. But it's just so clever. I mean, it's so elegant. That's the beauty of mathematics for me, is I see this elegance, and it's so simple, the whole thing. I mean, think about it, and you're going to hear me say this ad nauseum in calculus. The whole basis for this whole idea is to be able to take roots of complex numbers and be able to solve for all of them. And the whole thing came from a combination of Pythagorean's theorem, which produced the modulus in the complex plane, and then simple polar coordinates. I hope you enjoyed. It's been a good semester, at least it has for me. I don't know, I actually made these videos in advance, so who knows? I don't know. I made it about a month in advance, more or less. It could have been an awful semester, but hopefully not. I'll talk to you guys tomorrow in class. Have a really good day.